Tēnā koutou, kia ora koutou katoa. E nā manuhiri matararahi, e nā hoa mahi, e nā tōiara, e nā kaitotoko, mena ho. No mai haere mai ki te whare wānanga. Welcome to everyone, to all our guests, academic colleagues, students, supporters and friends, to the inaugural professorial lecture of Martyn Coles, Professor of Chemistry in the School of Chemical and Physical Sciences. Martyn, we've been looking forward to tonight for some time. As people will know, Martyn's professorial lecture was postponed last year due to COVID, so it's lovely to be here tonight. For any guests who might not know me, I'm Jennifer Windsor. I'm Acting Vice-Chancellor, and it's a real pleasure to welcome you here this evening. I'm pleased to be joined by colleagues from the senior leadership team and by colleagues from around the university. Professor Coles is a leading authority on the chemistry of the heavy main group elements in the periodic table. He specializes in the synthesis and reactivity mainly of metallic element compounds. Martyn joined the university in 2011 via Durham, Iowa, Berkeley, and Sussex. He was made professor here in 2019. I think Martyn is at the very top of his game. He's a prolific scholar, researcher, and grant awardee, and as one example of that, he won the 2011 Maurice Wilkins Center Prize for Chemical Science. He's equally well known, I think, for his dedication to teaching. He's seen as one of the most approachable lecturers that students could hope for, and he's passionate about sharing his love for chemistry with students. I'd also note in his former role as head of school, he's also made a key contribution, an administrative contribution, in supporting the school with all of its significant lab-based activities through the early stages of COVID. So who we have with us tonight is what I'd call as a triple threat type of scholar, whose contributions and achievements really do span research, teaching, and engagement. And among his achievements and his contributions, it's his scholarship that is center stage this evening. Most recently, Professor Coles' research has focused on finding uses for chemical compounds like the gases carbon dioxide and carbon monoxide in the formation of useful products. He's also an important voice in the technology and instrumentation that moves synthetic chemistry forward in New Zealand, perhaps especially related to X-ray diffraction to determine the accurate location of atoms in three-dimensional space. But to me, Martyn's work on the most basic elements and compounds of which all matter is composed has a great deal of alchemy. Beyond the highly productive and programmatic nature of his research, I think his scholarship has both beauty and power. Beauty in the exquisite nature and the precision of his calculations, as well as the simplicity of his visual representations of chemical bonding, power in his predictive argumentation and proofs, and in the linking of basic science and practical applications. I'm told that Martyn's passion for the periodic table and synthetic chemistry is contagious. That means we're in for a real treat tonight as he talks about his work related to that quite amazing atomic number jigsaw or Lego puzzle that is the periodic table and the new chemical compounds that can be produced. Nā ko te honore ki te whakauto, iene aharangi, Martyn Coles. It is my great delight to introduce Professor Martyn Coles.
It's great to see you. Thank you so much for being here. It's going to be an interesting talk, I hope, for you all. I have deliberately postponed this a couple of times due to my role as head of school, and I really wanted to get to grips with this and engage with this fully. And then, of course, it was cancelled through COVID. But I'm so pleased that we now have this live opportunity for me to present my work. So it's great to see you all. Interestingly, I'm going to begin with an apology. I haven't actually checked any copyright infringements. So when I refer to the periodic table with reference to Lego, perhaps I should be calling it the periodic table is my molecular children's construction toy consisting of small interlocking plastic pieces. I don't think that's quite as catchy, so I don't think there'd be as many people in the audience if I had called it that. So also, if there are any Americans in the audience, I apologize. I'm from the UK, as we'll find out. I refer to Lego as singular. I believe America is referred to as Legos, plural. And of course, we're now in New Zealand, and so I've gone with the UK pronunciation of Lego. Okay. So what's it all about then? I am a synthetic chemist. I make things. And the way that I make things is I join elements together. So you can see element A, element B, I combine them together and form a bond. Okay. And what I want to do over the next slide or so is show you how this can get very complicated very quickly. So here we've got element A plus element B with a single bond between the two elements. But there are other bonds. You can have double bonds, so I've got a double bond between them here, or even a triple bond. And of course, if we've got element A and element B, we can combine the A's together and the B's together. And then we can do that with double bonds and triple bonds. So even just a simple case of two elements and three different types of bonds, you can see the complexity is getting quite pronounced. Then what happens if we have another element? Okay, so now we've got three elements, two A's and a B, or two B's and an A, three A's or three B's. And then if we introduce the double and triple bonds to that, you can see things are snowballing rapidly. So how do we bring this all together? What happens if we start talking about rings? Everything I talked about so far was linear. What about if we start introducing other elements? Okay? And how do we get to the point where we can look at these complex molecules that we so much enjoy in our chemistry? Lego. Okay? This is what I thought might help us understand what I'm talking about and what makes me excited about my research. It wasn't the first analogy I came up with. I tried another couple on for size. The periodic table is my artist's palette, where I paint pretty molecules. But I've got terrible drawing skills. Talk to my family. I once drew a dog. It looked more like a pig. The periodic table is my chef's larder. Okay, so I think I can get away with cooking a decent meal. But then I thought, we tell our undergraduates no eating in the lab. So there may be a mixed message coming across. But the common theme here is we're combining basic ingredients, whether it's paints, whether it's Lego pieces, whether it's just basic ingredients, and we're going to make something more complex. Okay? And that's what I do, and that's what I want to talk about today. So the periodic table. Okay, so this is the official definition, according to the Oxford English Dictionary, of the periodic table. A table of the elements arranged according to the periodic law, one in which they are arranged in order of atomic number, usually in rows, such that groups of elements possessing analogous electronic structures and hence exhibiting similar chemical properties form vertical columns known as groups in the table. And this is probably what we're very familiar with, this kind of picture here. Now, there are other ways of representing it, but this is the one that I've chosen to use in this talk because I think it's one that most of you will be familiar with. And the things we need to know really is up here on the left, these are light elements. As we go down here, they get heavier. And then when it talks about groups, so as you go up and down here, these elements tend to have chemistry that's quite closely related. So I'm going to take you on a journey. I'm going to take you on a journey going back through my career as a scientist, starting to where it all began back in the 1980s. Now, I'm from the UK. I'm actually from place near Bristol, a small village called Winterbourne, and I went to Elm Park Primary School when I was, 8, 9, 10, 11 years old, okay, just down the road from my parents' house. And it was there that I probably first was introduced to the periodic table, and I first became familiar with it, just knowing what it was, maybe not knowing too much about it. But I think this is where my love for science really took off. And I thank, you choose, Mr. Moore. Okay, Mr. Moore over here. He actually did practical chemistry or practical science lessons in our primary school. And it was a comprehensive school. We didn't have access to great funds, but I've chosen 3 different experiments that I remember specifically from my time when I was about 10 or 11 years old. And we were doing a project on air pressure and changes in air pressure and what the effects of air pressure are. So these 3 experiments, just very quickly, over on the left-hand side, this is just a glass jar. You can possibly see in the bottom there are some matches. If you light a match and put it in there, the air rises, okay? So there's less air inside, more air on the outside pushing down. If you then take a hard-boiled egg that's been shelled, plop it on top, what should happen is the air pressure pushes it back down inside. Fantastic, great when you're an 11-year-old kid, really exciting. Now this is probably not familiar to some of the younger members of the audience. This is what we used to get our oil in, and it's a metal can. But exactly the same principle applies. Presumably you have to clear it out quite quickly before you put the matches in. But basically the air rises, less air inside, lower air pressure. If you screw the cap on, run it under cold water, it collapses as the air pressure pushes in. And then finally, we were actually made some hot air balloons using tissue paper and then put a little paraffin burner underneath to heat the air and cause it to rise. Fantastic. 3 things in common. They all involve fire, okay? So for an 11-year-old kid, seeing things burn is fantastic. So I guess I had a career choice to make at this. Was it the science that I was interested in, or was I a future pyromaniac? You decide. And I know you've all been looking at this photo thinking, where is he? Which one is he? Well, if you ever want to find me in a photo, look how tall I am. I'm always down the front. There I am. Who spotted me? Okay, so when I went to university in the 1990s, this was my periodic table. Okay, it looks familiar. It looks pretty much what I was talking about earlier. There were some unusual elements down here, though. UNQ, UNP, UNH, and UNS, which stood for Unyl quadium, unyl pentium, unyl hexium, and unyl septium. Okay? So these were relatively new elements. Remember, this is the 1990s, so some of them were only 10 years old. I went back to my textbook and had a look and see if I could see what they said about these elements at the time. So this is my undergraduate textbook, Cotton and Wilkinson, for those of you who remember that, for fermium and beyond, which are these heavier elements, fermiums down here. So for elements 100 onwards, only sub-microgram quantities down to 10 atoms or fewer were known. For elements 106 and 107, there were no chemical properties whatsoever known. And greater than 110, there was no evidence for them in nature or in the laboratory. Now, they'd been predicted. People had predicted these elements. They'd even come up with a nomenclature for naming them. And I particularly like these proposed names. Element 110, unylium, and element 111, my personal favorite, unium. That didn't stick. This is what the periodic table looks like now, and you'll notice all of these elements down here have been filled in. So elements 104 to 118 have now been synthesized. So these elements are made in synchrotrons by colliding other atoms together. Okay, so these are the dates in which they were made. And I think that just serves to prove the point that chemistry is still alive. Chemistry is still growing. If we're still adding things to the periodic table within my lifetime, since I went to the university, then the subject's not dead. It's alive. It's evolving. Where we go from here, I don't know. We've kind of run out at the end. But maybe in another 20, 30 years' time, we'll have some more elements to add. So what I want to do is take you on a journey, as I said, my journey through the periodic table. I'm not going to talk about all of the periodic table. There are some caveats to my journey. The first one being radioactive elements. Now, I've tried to avoid those because we all know radioactivity is bad, correct? Of course it is. Look, Homer Simpson's glowing. That looks pretty scary. So all of these elements that I've outlined here have no stable isotopes associated with them. So I've not done any significant chemistry with them. Now, I've said that elements have no stable isotopes, okay? So that all samples of those elements are radioactive. But there are other elements out there that have radioactive components, okay? Potassium. Potassium is an example. So we have different isotopes. Now, isotopes differ in the number of neutrons that are located in the nucleus of those atoms. So we've got 3 different flavors, if you like, of potassium. K39, K40, and K41. Okay, and they vary in the number of neutrons that they have. Now, 2 of these are stable, and these are the most prevalent ones. So 93% of the time, potassium exists as K39. The remaining 6.7, it's K41, and both of those are stable. But there is a small fraction of potassium that is radioactive, 0.0117% or 117 parts per million, then that's unstable and that will decompose. Thankfully, it has a half-life of 1.25 billion years, so we don't need to worry. But where do we find potassium? Bananas. Bananas are radioactive. But we don't need to worry about it because the amount of radioactivity is really small. And when I was researching this, I found out there's actually an unofficial unit of radiation called the banana equivalent dose. It's equivalent to 10 to the minus 7 sieverts, which is the more recognized unit, and it corresponds to about 1% of the daily exposure from natural background radiation. We're exposed to cosmic rays, we get radioactivity from various other sources. So it's about 1%, meaning 100 bananas. You had 100 bananas, it would be your normal daily exposure to background radiation. Personally, I think if you ate 100 bananas, you've got some more trouble on the way. So we're not going to talk about radioactives. What about the non-reactive elements? Okay, so over here on the right-hand side, we have what we used to call them the inert gases. Now, we are aware of them. We've seen them. We've seen neon signs. We've seen helium balloons. But these aren't actually chemistry. We're not forming bonds to these elements. We're not breaking bonds to these elements. These are just using the elements in their elemental form. I'd like to point out this picture here, actually, and thank Cara, who I think is at the back there. This was a celebration for my 50th birthday when I was head of school, opening the office door, finding helium balloons everywhere. And the great news is we used our helium recycling unit down in the basement of Leiby, which we used to recycle helium for our NMRs. So we didn't even have to spend money. Perhaps that's a money-making scheme we could use later on. Okay, so they're not inert gases. We now refer to them as noble gases. And it's actually 60 years ago that this guy here, Neil Bartlett, made the first compound that involved one of these elements. Up until that point, people thought they were just inert. There was no chemistry associated with them. 60 years ago, Neil Bartlett proved that that wasn't the case. Another example of chemistry evolving, of the periodic table expanding, if you like. Okay, so back to me, back to my journey, where it all began, Durham. So I did my undergraduate degree and my PhD at the University of Durham. And I focused on these three metallic elements, vanadium, chromium, and molybdenum. I used other elements as well. I didn't just use the metals, and we'll talk about that in terms of the sorts of chemistry that I developed while I was there. So this is my snapshot of my time at Durham. So I want to point a few things out. Those of you who don't know where Durham is, it's in the northeast of England, about as far away as I could get from my parents without hitting Scotland. The university is a collegiate university, so there's different colleges. I was a member when I was an undergraduate, and I guess I still am a member, of University College, which was based in the castle. So in my third year as an undergraduate, I got to live in Durham Castle. This is the keep. My bedroom was round the other side, looking out that way. I played darts. In fact, this tie is my college colours for playing darts. This is the pub we used to practice in. Interestingly enough, that pub doesn't have a dartboard. You can guess what we were practicing. This is my first paper, and this is my first crystal structure. That's what I looked like when I went to university. You can see my hair has got big. Okay, so what did I research? And this is where the Lego comes in, and this is where I hope to explain some of the sorts of things that I've been involved in. Metal complexes as reagents. So they can be used for forming bonds. So we can bring two Lego pieces together, click them together, form a bond between them. Or we can use them to come apart. Now, we don't do that with just atoms. We do this with molecules. We do that with a specific point within a molecule, an atom within a molecule. So again, we can join them together. So this is just sort of a more realistic representation of what we're doing. And we form a bond between them. Okay? And that, in a nutshell, is what I do. But you'll notice I had this MLX. And that's where my research has been focused for the last too many years, 30 years or so. So what is MLX? It's a metal complex. Okay? Now, a metal complex consists of a central metal atom, and to that metal atom we put groups around it. And we call those groups ligands. I'm just going to denote them as L at the moment. And it's through controlling these ligands we can dictate how the chemical reactivity of those metal atoms behave towards different substrates. And so by changing the ligands, by tuning the ligands, we can control the reactivity. It is a bit of a black box sometimes. Sometimes all we're interested in is taking the two things and seeing what comes out the other side. But what I want to do as a scientist, and what I've been doing for the years, is opening up that box and having a look inside, peering in and seeing if we can understand what's going on. Because if we can understand, we can change it, we can make things better, we can control different things. So back to my PhD. I did my PhD with Professor Vernon Gibson. It was sponsored by BP Chemicals. And we were involved in ethylene polymerization catalysis. So there was a lot of research at the time that it was involved in making polyethylene or polythene using ethene as a gas. And the state of the art involved this zirconium compound here. So this is now basically our metal is zirconium. And these groups around it are just our ligands. Okay? Now, two of those ligands, these sort of funny cyclic ones at the back here, they're just there to support the metal, and the other ones are where the chemistry goes on. So my research was involved in looking at other metals and how we can change other metals to see if we can affect this reactivity. So I focused in on chromium. So chromium is now in group 6, so it's in a different group in the periodic table. So it has different electronic structure. And so in order to try and mimic the zirconium, which we know works, we have to change our ligands. And so, in this case, rather than having these cyclic ligands, we have these nitrogen-based ligands, where this N atom is nitrogen. And you can see we've got a double bond now. So we've moved away from single bonds to double bonds. Thankfully, it worked. So if you activate this compound and expose it to ethylene gas, you produce polyethylene. Okay? So we were quite happy with that result. What we're doing, we're taking lots of different lots of the same Lego brick. So these are our ethene molecules. And we're stringing them together. We're forming lots of different bonds. And we're using this, which is our black box, where the chemistry is going on. Now, I just want to take a moment to refer to some of the techniques that we use in our research. And as the acting Vice-Chancellor mentioned, crystallography is one of my passions. So crystallography is a technique we use to analyze solid-state materials or solid-state compounds. And think about a grain of salt. Think about a grain of sugar. That's a crystal, okay? That's a single crystal, hopefully. And what we do is we take that and we put it in this tiny little place here, which is buried in here, and we shine X-rays at it. And the X-rays interact with those atoms and they diffract. And then we measure the diffraction pattern here, and then we press lots of buttons on computers, and what we end up with is, from our chemical drawing, what we think we've got, we end up with a crystal structure. And this shows us where these atoms are in three-dimensional space. Now, why is that useful? Well, if you compare these two drawings, that's what I said my compound was. But if you look at how the atoms are arranged in the solid state, you'll see that there's two lines between these carbon atoms. So this is carbon, the white spheres are hydrogen, so that's a CH2. This is a pH, and we see there's two bonds. So by determining the crystal structure, we know that the bonding is slightly different to how I wrote it out in my chemical structure. We can also give better representations of the atoms. Atoms are actually quite large, and so we can do what's known as a space-filling model. And if we do a space-filling model, we can see buried down in here, that's where our metal is. So the ligands are protecting that metal. But is there then enough space for the substrates to get in? Because remember, the chemistry that we're interested in is going on at that metal center. The ligands are around there to control the chemistry. And finally, it allows us to do really pretty pictures for presentations. And if you had any idea how long it took me to do this, you'd appreciate it as much as I do. Okay, one thing I should say, when I came to Vic, we didn't have an X-ray diffractometer. But through the generous support of the CAPEX, we were able to get one. And it was installed 2017, I think it says it there. Yep, 2017. So it's been going for about 5 years, and it's been churning out results, and they've been included in many, many papers. So I consider it to be a good investment, and it's essential to not only my research, but to several other groups in our school. It was fortunate that we were able to tie in the dedication of this to the 60th anniversary of Emeritus Professor Neil Curtis, and we were dedicated that room, the X-ray diffraction facility, I should say, to him to commemorate his 60 years. And so I just wanted to mention that. That was one of my most pleasurable roles as head of school. The other thing I should mention about the chemistry I do is it's air sensitive. Okay? What that means is air is a mixture of gases. One of the gases is oxygen. There's also water vapors present in air as well. And both of these compounds, chemicals, elements, are highly reactive towards the kinds of things that we make. So we have to take precautions. We have to protect our compounds from coming into contact with the air. And we do that for through various means. We do a lot of our work in a glove box. So this is, sorry, I forgot what button I was pressing there. This is a glove box. So this is a box filled with nitrogen gas. Now, nitrogen gas doesn't react with our compounds, usually. And so the gloves stick out. You put your gloves in and you do all your chemistry inside this protective atmosphere. You'll notice here that these are our NMR tubes. These are all got sealed tops. This has got a sealed top here. This is a vacuum line. So we have to protect everything from air at all times. We don't just stir our chemicals over a beaker. So it's quite challenging to do this kind of chemistry. Okay? But I think it's thoroughly rewarding when we get something that works. Now what I want to do is just show you, this should be a little video, I hope it works, what happens when we don't protect our compounds. So what we've got here is, this is a student inside this glass vessel. You can just about see here, there's a compound. It's connected up to the vacuum line, so all the chemistry so far has been done under an inert atmosphere, but he's about to take the top off, and if you see what happens, when it came in contact with the air, it caught fire immediately. So that gives you an indication of how sensitive some of our chemistry is. Now I want to watch this one more time, because I want you to see how efficient he is at putting the fire out. Look at that, one hand putting the top back on, other hand reaches for the oven mitt, and then he places that on top of the fire. Very controlled, very sensible way of doing it, snuffed that out immediately. And I would also like to point out, he knew that was going to happen, he was prepared, we have other people in place, it's all done very safe, and that video was actually slowed down about 2.5 times. So he's doing this instantly. He's a very talented PhD student. Possibly even in the audience. So, I left Durham. I have my thesis, Transition Metal Imido Compound Synthesis and Applications to Polymerization Catalysis. Occasionally I get it out and show students how not to write a thesis now, but other than that, it sits on my shelf with my other ones. And there you go. Still got long hair. Off to get my BTA degree. Now, my BTA degree was a kind of a standing joke we had. If you wanted to get an academic job in the UK, you had to get a BTA degree, been to America. So I went off to America. My first stop was in the Midwest. Anybody recognize which state that is? Iowa. I heard someone mention it. And I spent 2 years in Iowa working with Professor Rich Jordan at the University of Iowa, where I worked on similar kinds of chemistry. So it was again looking at olefin polymerization catalysis, but now we're moving away from transition metals and looking at main group compounds. So this is aluminium. So again, we're changing the metal. If we change the metal, we need to change the ligands to try and recreate the kind of chemistry that we observed for the other systems we looked at. 2 years, great time. Then I went to Berkeley. Spent another year and a bit there working with Professor T. Don Tilley. And I changed strategy a little bit there. I looked at, again, kind of similar. So you can see this is a molybdenum compound. These are some ligands around it. But we took these as precursors to materials. So we designed our molecules. We carefully synthesized our molecules. We protected them from air. And then we decomposed them deliberately to give us a material. But by looking at the material that was formed, it had molybdenum in there, it had other elements, and then we tested that material for catalysis. So much more solid state exposure there, which has proved really useful now in the current school that we're in. Okay, so I can cross a few more elements off. So we had vanadium, chromium, molybdenum. I've crossed a few more off at this point. Then in 1999, I joined the University of Sussex, my first independent position. Okay. Now, back in the UK, here's London, here's Brighton. So the University of Sussex is on Falmer campus, just outside of Brighton. It's a wonderful place out near the Downs. Interestingly, this is the plan view of the campus. Now, if I stand here, you might be able to just make out sort of a pair of ears and a head going down here to a tail coming out. There's a paw down there. It's actually a plan view. That was designed by Sir Basil Spence, famous for the beehive. And he planned the campus to look like a cat. Other things. There were 2 Nobel Prize winners in the department when I joined, Sir John Cornforth and Sir Harry Kroto. The other thing Brighton's famous for, Brighton Pier. This is what Brighton Pier looked like when I arrived. Unfortunately, there was a storm. Then, unfortunately, it caught fire. And this is what it looks like now. But it has a certain beauty to it now. It's just got the iron frame left. And what you find is at night, the starlings roost out there. And so if you get the timing right, they have that wonderful flying, it's got a name. Thank you. It has that thing where they all fly around and look really cool. There's me. Got a haircut. Didn't get a shave though, did I? So I did lots of projects. I'm not really going to talk about them because I do want to spend some time talking about the research that I've been doing recently. Lots of projects looking at different ligands, different metals, different reactions. But the common theme is we've got metals surrounded by ligands. So again, we're just adopting this technique. Most of the chemistry I'd done up to that point involved the transition metals, these D-block elements in the middle. But there was I guess there was a sort of a move towards looking at other metals. So you saw I'd looked at aluminium. So there was a lot of research that was going on in trying to replace these transition metals with some of these main group metals from other places in the periodic table. The reason being sometimes they're cheaper, sometimes they're more earth abundant. So a lot of elements here, so platinum, rhodium, iridium, very expensive, very difficult to get hold of. And so if you're going to do an industrial process using these precious metals, then it's going to cost a lot of money. And there's also environmental impacts that people have to consider as well. So if you can do similar chemistry with some of these cheaper metals, aluminium, calcium, magnesium, then perhaps that's a way forward where this subject can evolve. So I want to talk about heavy metal. Yeah, that was me. Bismuth. So this is where I started my research in main group chemistry, looking at heavy elements, bismuth. And there was a couple of reasons. The first one being it was really underdeveloped. So these pink areas at the top here are relative numbers of crystal structures in the database that I use regularly. And you can see that these are smaller compared to the other colors. So they're smaller compared to the blue and the red. And that's just basically saying that there was less research that had been done, or one way of measuring the amount of research. Now, I chose bismuth, even though it's a heavy metal, it's what we consider to be non-toxic. Now, that's very unusual for this element, because if you look at what it's close to in the periodic table, it's near mercury, thallium, and lead. And these are known to be toxic elements. But bismuth itself is non-toxic. I put non-toxic in inverted commas because someone may pick up on this. It actually is toxic to certain bugs, but for the purposes of this talk, we'll consider it to be non-toxic, certainly less toxic than the other elements. And so it has potential use in chemistry. So if there's a little bit there, then we can kind of ignore it, if you like. So this was a target compound, and then very quickly, bismuth, 3 groups around it. I was trying to make this sort of linked ligand. Don't worry too much about the charge. So just look at the shape, 3 atoms around here. This is to support the compound. This is to support the bismuth center. This is where the chemistry is going to go on. And that was the design that I had to look at. Now, around about this time, I went on a short flight from London and I relocated over here in New Zealand. So the chemistry I'm going to talk about from here on in is pretty much what we've been doing since we've been at Vic. So we looked at different ligands. So again, this is now just more detail around what we were talking about. So this is what the actual compound is. We've got these dip groups, which is this organic substituent here. We've got our 3 groups around bismuth. But we have to consider 3-dimensional space, remember. Molecules have 3 dimensions, and so it's not a flat molecule. You can see it's like this pyramid. It's like this tripod. We also looked at this 6-membered ring. So this is 4 atoms in a ring. This is now 6 atoms in a ring. And so what we've got here is an opening up. And if you look down that metal X bond, or the bismuth X bond, so this is now just looking down on top, you can see what happens to these groups. Going from a 4-membered ring to a 6-membered ring really pushes these groups around that metal. So by changing the ligand, we're changing the environment at that metal center. So I want to quickly talk about main group radicals. The electronic configuration of bismuth looks a bit complicated. Don't need to worry about those. Those are core electrons. Those don't take part in the chemistry. These are filled orbitals. They're, again, very stable. What we're interested in is those electrons which we refer to as the valence electrons. And you'll see there are 2 in what's known as an s orbital, and 3 of which are what's known as a p orbital. If we remove 3 of those electrons are negatively charged, the bismuth atom picks up a +3 charge. You remove 3 minuses, it's got +3 left. If we remove all of them, it's got +5. But what we found in our research is if you react this compound here, so this was the one we saw on the previous slide, with just magnesium metal, we can actually push it into an unusual oxidation state. And the unusual oxidation state is +2. So this is now got a lone electron, an unpaired electron. And this was the first time that this had been observed on a heavy element. They tend to be very unstable, very reactive species when they're on heavy elements, if you've got a radical, an unpaired electron. This is what it looks like. So again, you can see we've got the six-membered ring, but there's only two coordinate at bismuth, there's nothing else. And we proved that by various other analytical techniques. But what's the big deal? Well, now we've changed the electronics at that metal center. It's got that one electron left. So can it do some interesting or unusual reactivity? And the answer is yes. There's two examples. I'll just talk about one. I'll brush through the other one. But this is white phosphorus, okay? So white phosphorus consists of a tetrahedron of 4 phosphorus atoms. And all of those phosphorus atoms are equivalent. So we examine this using a different technique called NMR spectroscopy. And this is an example of a series of NMR spectroscopy from a mixture of P4 and our bismuth radical. All you need to know is the number of peaks tell you the number of phosphorus environments, and the shapes or the patterns of the peaks give us a little bit of information about how those atoms are bonded together. So just point out this line here as a standard so we can all make sure that it's all lined up and compared. So we ignore this peak. At 20 degrees centigrade, we see just a single peak for our P4. So all of those phosphorus atoms are the same. And that corresponds to no reaction. But as we cool it down, we can see these new peaks growing in. 2 different peaks tell us there's 2 different phosphorus environments. And if we look closely, we can see that these are triplets, and that tells us something about the way in which they're bonded to one another. If we get the crystal structure, this is what we find has happened. So we've now got 2 bismuth atoms that are bonded to our central P4 unit. But what's happened is we've broken one of the bonds. So you can see, hopefully, that blue phosphorus is the same as that blue phosphorus because they're both bonded to the bismuth, and then those two are equivalent as well. So they're related by symmetry. So we consider them to be the same. So we've got 2 different groups of 2 phosphorus atoms, which explains our NMR. So what we've done is with our bismuth, we've taken a bond that exists between these 2 phosphorus atoms, and we've broken it. So we've now taken apart our 2 Lego pieces. I'm going to skip through this one because time's getting on. But I want to talk a little bit about aluminium chemistry. So that was bismuth. I now want to talk about aluminium. So aluminium, using the same kind of argument, is a lighter element. So we're now looking at a different type of chemistry. So we've got some core electrons still. Don't need to worry about those. Let's look at the valence electrons. Total of 3 in 2 different groups of orbitals. We can remove 1 or we can remove all 3. Now, aluminium mostly removes all 3 of those electrons to give a +3 oxidation state. And that's the most stable. And when aluminium is in a +3 oxidation state, it's hungry for electrons. It wants electrons back. So we say it's electron deficient, and it's there to take electrons from different substrates. And that's what dictates the chemistry. But what we did was we developed an aluminium-1 compound that has a dianionic ligand that really pushes electrons back onto that aluminium. So now we've got, excuse me, if I can go back. So now we've got, that one there. We've got this electron configuration. So we've taken just 1 electron away, so it's aluminium-1, but we've got the same ligand. The same ligand that has 2 minus charges. So overall, the aluminium has a negative charge. And that's an aluminyl anion. And that was the first time there was a group in Oxford working at the same time as us, and we were the first groups to discover this type of compound. And what's so fascinating about this compound is we've now got an electron-rich aluminium system. It's got a lone pair of electrons. So we've taken an element that normally behaves as electron deficient, loaded a bunch of electrons on, and now we can look at the chemistry where we've turned it on its head, and it's an electron-rich compound. So this is what it looks like. Because the aluminium is negative, we need to have a positive cation, because overall it's neutral, and the cation we have is potassium. And you can see that we've got 2 aluminiums, so 2 minuses, so we have 2 potassiums. And they're sat between these 2 compounds, and in the solid state, it's held together like this, positives and negatives attracting. So this is where we look at the reactivity. So we take this compound, which we've turned the reactivity on its head, and see how it reacts with different things. So this is carbon dioxide. Now, I'm not going to claim that I'm going to solve the world's climate change problem. But what I want to do is look at how fundamental chemistry can be governed by these metal compounds. Again, peering into that black box, having a look, see what goes on. And what we found was, if we take our aluminium compound, react it with CO2, we make a carbonate. Now, a carbonate here, you can see we have a carbon atom and 3 oxygens. So it's reacted with, it can't have all come from carbon dioxide because we've got 2 oxygens here and 3 oxygens there. So something's going on. But what we showed by opening that black box, having a look in, is it reacts with 2 molecules of carbon dioxide. The first one comes in, gives up one of its oxygens to generate this species here that has an aluminium-oxygen double bond. And we were able to make that independently via a different route. We were also able to detect the carbon monoxide that comes off. Once we've got this compound, it will react with another equivalent of carbon dioxide. So overall, we're taking 2 equivalents of carbon dioxide, producing 1 equivalent of carbon monoxide, and making this carbonate. It actually tetramerizes, and this is, going back to what the acting Vice-Chancellor said, the beauty of these molecules. This is what I consider a beautiful molecule. Okay? So it forms 4 of these groups that come together, and they are held together by these positive and negative interactions between the anions and the cations. So what we've done in terms of Lego, taken 2 carbon dioxides. We've broken one of these carbon-oxygen bonds and formed another carbon-oxygen bond. So we've got a system now where we've broken and formed bonds in the same reaction. Cool. Well, I think it's cool. The last reaction I want to talk about is carbon monoxide. So carbon monoxide is the strongest bond in nature. Okay? So that's a real challenge. That's a red rag to a bull as far as I'm concerned. If we can do something with these really strong bonds, then the world's our oyster. And what we found was if we take our aluminyl anion and react it with carbon monoxide, what we can do is start to string them together. So we can start to form chains of molecules. So just reacting this with carbon monoxide, and this is at room temperature, at normal pressure, just 1 atmosphere of carbon monoxide, you can see we've formed a C4 chain. So 4 carbon atoms have come together. We can take that 1 step further. We change the conditions. We actually change this reagent a little bit. And what we've got now is 5 carbon atoms that have formed, or 5 carbon monoxides that have formed a C5 chain. Okay? Now, why is that important? There's an industrial process called the Haber-Bosch process, which takes carbon monoxide and hydrogen, and it combines them together under extremely high temperatures and extremely high pressures, and it forms chains of carbon atoms. And then these go on and are used in fuels and cosmetics and other fine chemicals. So if we can start to understand, and if we can do this, like I said, room temperature, normal atmospheric pressure, then we can start to understand the chemistry, and perhaps we can do something with that. Okay, so just very quickly, if I may. I'm not sure exactly what time we started, but I just want to talk a little bit about academic research. I'm an academic. I consider myself to be extremely privileged to be in a position where I can do blue skies research. But I think it is fundamentally important to not only academia, but to society. Because without the fundamental research that goes on, what are people in the future going to look back at? And I've got a couple of examples. So this is C60. This is Buckminster fullerene, which was made by Harry Kroto at Sussex, one of the guys who got the Nobel Prize. And at the time, it was the 3rd form of carbon. So it was just another allotrope. A fantastic discovery, don't get me wrong. Really interesting discovery, but no practical use. Nowadays, derivatives of this are used in solar cells for the conversion of sunlight to electrical energy. So from 1990 to 2022, it's found applications. Similarly, Arduengo made a stable crystalline carbene compound. Carbenes have a 2-coordinate carbon atom. And at the time, it was just a challenge. No one had done it before. And now this is used as a ligand in many, many catalytic processes, some which are used on an industrial scale. So we've gone from having simple bricks to making basic structures. But what I've been trying to do, and what I want my legacy to be, is to take those simple bricks and make more complicated bricks. Because once you've got more complicated bricks, you can make more complicated structures. Okay? That's actually a life-size Bugatti made out of Lego. And it moves, apparently, according to TikTok. So I may not be in a position to do this, but I think I can concentrate on doing this so someone can take these parts and use them for the future. I've got a very quick thanks, and then I just want to summarize one last thing. PhD students, I apologize if I've left anyone off this list. It was a bit of a hurry today. They're the ones that do all the work. They're the ones that really push this research forward. And again, it's a privilege and a pleasure to work with young minds and to train them and to see them grow and develop as not only as scientists, but as people and as individuals. Collaborators, technicians. Let's not forget the technicians, the people that keep the instruments running. Without those, I would not be able to do any of my research. So absolute heartfelt thanks. Bit of funding here and there. And of course, my family. They've been behind me all the way and they've supported me through this. So thanks to Robin, thanks to Tristan. This, I believe, was taken at the top of Macra Peak. One of the good things about lockdown was we could walk up the mountain bike tracks without fear of getting killed on the way down by someone hurtling down vertical cliffs. So just very quickly, last minute, I promise. Periodic table and me. I reckon I've used all of these elements now in my career. If we add a few more in, so I've run crystal structures for other people, so they've done the chemistry, I've analysed them using crystallography, there's a few more we can cross off. You'll notice, actually, I've done some crystallography on thorium and uranium as well. Depleted. What's left? So these are the elements that are left. I'm going to cross those off. The common thing about beryllium, arsenic, osmium, and thallium, they're toxic and nasty, which leaves just these. These are my remaining goals. I've got a few years left in me yet, so watch this space, and hopefully one day I'll be able to report some chemistry involving these elements. So thank you once again. It's been a pleasure talking to you, and I hope you've enjoyed my journey through the periodic table. Thank you very much. Thank you.
Wonderful. What an amazing presentation. Thank you. It reminded me of when I was doing chemistry, and then a lot of things that I didn't understand even at that time, but that was brilliant. Tena koutou. My name is Ehsan Mesbahi. I'm the Pro Vice Chancellor of the Wellington Faculties of Science, Health, Engineering, Architecture and Design Innovation. And it's my great pleasure to give the vote of thanks to Professor Martyn Coles for tonight's lecture. Tonight we have had a glimpse of Professor Coles' passion for synthetic chemistry. We have heard about this journey towards understanding how the different pieces of molecular puzzle fit together to solve numerous problems, whether it be curing a disease or fighting climate change. I'm impressed by the breadth and application of his work, and tonight's lecture is a perfect example of his imaginative and impactful approach to science. There's still so much to be discovered in chemistry, and I know Professor Coles values the ability to undertake fundamental research that forms a strong foundation of knowledge for future generations and for the future industries and applications. I think it's very clear that Professor Coles is an incredibly dedicated teacher and supervisor. He is aware that the role of a teacher is an immense privilege and honor to both educate and enthuse future scientists and to give them the opportunity to be part of groundbreaking research, and also to contribute to be part of a team and work together at a global level. I'm sure that being a student of Professor Coles has been an exciting and inspiring experience for many of our young people. As the Vice-Chancellor noted, Professor Coles has received numerous accolades from his peers and from all around the world. A recent one I know he is particularly proud of being awarded the 2021 NZIC Maurice Wilkins Centre Prize, the premier prize of the New Zealand Institute of Chemistry, awarded to a candidate based on the excellence and impact of their chemistry. I think we can all agree that tonight Professor Coles has shown why he was awarded such a prestigious prize. I would like to acknowledge Professor Coles' wife, Associate Professor Robin Fulton, and his son Tristan, who have joined us tonight, and I'm sure they are immensely proud. Martyn, it's a pleasure to congratulate you on a fantastic inaugural professorial lecture. I would like to invite everyone tonight to join us in the common room outside for some refreshments. And first, please join me in thanking Martyn again for a fantastic lecture tonight. Thank you.